towards the end of the last session was have a look at three resistive loads of 1950 ohms connected in delta, and that just so happened that on the rig over there I got switchable resistors, and one of the options is 1950 ohms. So the idea of doing that was that we could actually set up and take the measurements on there and compare them with our calculations and see whether our calculations are right. So that's the idea of choosing those. So connected in delta to three-phase line voltage, 300 volts, 50 hertz. Determine the current in each load, so the phase current. Determine the line current. Determine the total power dissipated. Yeah. So we went ahead. We drew the system, because that's what's the recommendation that I always say. Draw the system. You can see what's going on. Okay. I mean, I make no apologies for using the old colours, red, yellow and blue, because they're the colours of the leads I've got over there anyway. So that's the system. Red, yellow and blue, 300 volt phases feeding into delta connected 1950 ohm resistors. So we've got three line currents IR, IY and IB, and three phase currents I1, I2 and I3 through the loads. We then went ahead and said all the loads are equal, and therefore, calculation-wise, in theory, I1 will be the same as I2 will be the same as I3. So we only need to calculate one load current, because that's balanced and all the loads are the same. We went ahead and calculated I1, which is, if we look at the diagram, each single resistor has got the line voltage across it, this 300 volts. So we used the line voltage and the value of the resistor to calculate the current flowing in each resistor, and we got 150 milliamps. Later on, at the moment I've got the rig set up in star, but later on I'll connect it up in delta. We'll be able to confirm those results. Hopefully we'll have time to do that. Alright, then we used the formula. We said the system is balanced, so the line currents, I red, I yellow and I blue, should also be equal to each other because the load's balanced. And therefore, we could find IR from I1 times the root of 3. So we go on from phase current to line current, it must get bigger, 260 milliamps. And then total power, so we calculated the power, the line voltage times the phase current gives the power for one load, multiply that by 3, gives you the total power. We got 132 watts. Okay, what we'll be doing when we do it on the rig is we'll measure the power for each load. I've got watt meter connected to two of the loads. I've only got 2 watt meters, but we'll make the assumption that the other one's the same. You'll see that they aren't exactly the same, and that's because of component tolerances, but they're close enough to confirm these results. Okay. Secondly, at a balanced star system, the same loads. Calculate the current in each load, calculate the total power, calculate the current in the neutral. For each load from that, This board is starting to get on my nerves. To find the total, multiply that by 2. Finding the neutral, need Kirchhoff's going back to the diagram. Each of these currents here are flowing into this node, are all going into it. So if that 3 are going in, the neutral one must be going out. And all the currents going in should add up to the currents leaving. There are no leaks. That's the basis of Kirchhoff's current law. So we need to add them all together and see what they add up to. An electrician in the room, Lee, told me there's no current flowing in the neutral, and he's right, but we're proving it. But to do that, we have to add the currents up in their complex form, because although they're 88.8 milliamps each, they're all 120 degrees out of phase with each other. So you had to take one phase as 88 milliamps at 0 degrees, another one at plus 120 degrees, and the third one at minus 120 degrees, convert them all to rectangular numbers, add them up, and they then approximate to 0 plus 0J amps current, Michael. Yep. So if you have a perfectly balanced 3-phase star-connected system with a neutral at the center point, that's perfectly balanced, you will get 0 current flowing in the neutral conductor. Okay, so we'll just pause that there. The load. Bear in mind that it's the phase voltage over the resistance, because that's the phase voltage across each load there. We get the phase voltage from the that by the particular 182 milliamps, 46 milliamps. You need to do for the number. We got to take into account these angles, yeah. So that's arbitrary, but we need to take into account, let's write that down, need to account for phase shift equal to 182 milliamps. Which one we picked? 0, just is equal to 89 milliamps, angle 120 degrees. If that's the case, you need to say that IB is 46 milliamps, an angle minus 120 degrees. And we need then to convert all of those to rectangular numbers so that we can add them together and come up with a value for current. So I'll let you do that. So we've got to do 182 minus 44.5 minus 23. And 77.1 minus 39.9. Yes. Yeah. This is the answer in rectangular form, but I've not got a meter that will measure in rectangular form, so we have to go back to polar form, alright? So we're taking, Richard, guys, we're taking the individual currents, not easy we've got them in polar form, but you're not going to add all those together in polar form, too difficult geometry wise. So we convert them to rectangular form, add them together, and then convert them back, and we got our neutral current that we can now go over on the rig and confirm.